This is a short video about radius of curvature. Here's the formula off the web. It involves the first derivative squared and the second derivative. So I've got a cubic curve here. I've got the first and second derivatives plotted, and you can see that I've managed to create the radius of curvature, which will be a minimum at the maximum point here. Something very special happens at the point of inflection, where it switches from one side to the other, and minimum again at the minimum. So that's it working. Let's just see how it all gets put together. Over here I've got the cubic curve, and now I'm going to do the first derivative and the second derivative. And I'm going to put a point on the curve, and through that point I'm going to draw a vertical line and also a normal, which I'll use in a minute. The vertical line cuts the first derivative here and the second derivative here. I want to find those points, so I'm going to go to intersection. Here is the intersection with the first derivative, and here's the intersection with the second derivative. So we now know the value of y dashed and y double dashed at this particular value of x. As we move this around, so it's going to change. So what I want to do now is allocate constants to these two values, which I do up here in the manage constants. So I'm going to choose A, and I want an attribute for A of the y value of this point here. That'll be the first derivative. Add that in. Then I want the second derivative to be associated with the letter B. So I'm going to go down here, and there it is. So we've now got A and B fixed. It means I can work out the formula. Now before I open up the calculator, I need to view the keyboard, because I'm probably going to have to need this for squared. There it is. Lovely. So here's the calculator. The formula is 1 plus, now it's going to be absolute value first of all, open brackets, 1 plus, now y dash is just A squared, is squared on here, close brackets, raised to the power of, open brackets, 3 divided by 2, close brackets, divided by the second derivative, which is b, and then the absolute value finishes off at 2.818. Click OK. That's not very interesting, so I'm going to double click on that to take us back to here to put r equals space, and copy this formula, copy here, space equals space, so that on the diagram we've actually got the information you want. Now we want to create a vector along here that is of length r. So we need to associate r with this result. So I'm going to go back to this again and choose an attribute for the letter r, and that r will be the result of this calculation. Perfect. Add it in, close. Okay, now how are we going to make a vector of length r along here? So what I do first of all is put a random point anywhere along here. Back to select mode, select and right click, vector, 2 points. Okay, now I'm going to select this vector and this point and create a unit vector, unit vector, so that all I have to do now is scale this unit vector up by r, and I'll get a vector of the right length. So let's just get rid of some of these bits that we don't want that, and right click, hide, don't delete of course, hide. Okay, select the unit vector. It is a unit vector. If you just like to check that, it's just the same length all the way along. So select the unit vector, select this point, and do a multiply vector of length r. Okay, now r is 4.9, so it's going to be down here. That's about right. So is it working? Let's have a look. It's pretty good. There it is, the minimum there. That's just what we wanted. But I think we're going to be in trouble when we hit the point of inflection, where it's very, very long. It's infinitely long. Effectively, now it ought to jump to the other side, then it doesn't. Now it's well known from elementary calculus teaching that the second derivative is linked to the curvature of the parent graph. So when the second derivative is negative, it means that the gradient is decreasing all the time, and so you get a maximum. And when it's positive, it's increasing and you get a minimum. Now the second derivative has been given the letter b, and its sign has been taken away from it by the modulus signs in the formula. So the best thing to do is to move the absolute value 2 places to the left. So we'll double click on this to reopen the calculator, and we'll move the modulus sign 2 to the left. So shift, there it goes. We'll also do it here so that it displays correctly. Okay. Right, now it's good, except it's the wrong side, but while we're at it, I think we'll just get rid of these two, hide them. I think it's going to switch though, isn't it? Yes, it still switches, but it's just the wrong way around. So we just need to double click on this and change it from +r to -r, and that'll do the job nicely. There we go. And as we swing this round here, it switches nicely, and look at that, fantastic. What you can do, of course, also is put a circle on this. That's a center and point, and right click, circle, center and point. Now you can see that the concept of the radius of curvature is that it is the circle that has the same curvature as the parent graph. We move that around there, and that works very nicely. Now we could change the equation. It's a cubic at the moment. If I double click on this and change it to sine x, and let's see how that copes. Alright, there should be a switch every time there's a point in reflection, and sure enough, that's all very satisfactory. So it's a really nice example of the use of attributes in autograph, and these two objects up here, the managed constants and the calculator, very, very useful, and it's a lovely topic.